Today we are going to go over a very simple shape optimization with Nastran Sol 200. This is what you can expect in this exercise. We're going to take this cantilever beam and we're going to let the top and bottom of this cantilever beam vary. And our goal is to minimize the mass from 80 to a new optimal mass of 36.77. As for how this cantilever beam is loaded, we're going to fix one end of this beam and we're going to load the free end of the beam. And this is our optimization problem statement. We want to minimize the mass while constraining the von Mises stress to be less than an upper bound of 200. Now, we're going to create two shapes. This shape is going to contract this region of the cantilever beam. So let me go ahead and draw what that shape could look like. So we're going to either expand or contract the shape, and we're going to create a second shape that's going to expand or contract the second region. So hence we're going to have shape 1 and shape 2. Although it's not shown, we also have element faces selected in the bottom of the cantilever beam. Now as for the bounds, this is how you're going to interpret the bounds. We're going to go from the original boundary and we're going to contract the boundary by some delta. We're going to say delta equals negative 1.5. And this is approximate. So we're going to either contract these shapes by at most negative 1.5, or we're going to expand the shapes by at most 0.0. Since we're expanding by 0.0, that means we're not expanding at all in this exercise. So now let me move on to the next slide, the appendix. So if you're new to shape optimization, there might be some questions you might have. If you refer to the appendix, you will find a lot more information on how shape optimization is performed by MSC Nastran Sol 200. So if you flip to the very end of this presentation, you'll find the appendix where you can learn more about shape optimization. So now let's go ahead and go back to that previous slide and we'll continue on this tutorial. Now, just in case you want to learn more, just in case you want to learn as much as possible about gradient-based optimization or machine learning, you're more than welcome to contact me at this email address, and I'd be more than glad to work with you on automatically optimizing your structure or your mechanical system. Now, one quick comment. The Sol 200 web app is a collection of web applications all designed to help you optimize your Nastran model. If you can optimize your Nastran model, you can optimize your real-world structure or mechanical system. If you want to use Nastran's gradient-based optimizer, there are web apps to do that. There's a web app for size, topometry, and topology optimization. There's a web app for shape optimization. If you're dealing with a laminate, a composite laminate, you want to optimize the ply shapes, you want to optimize the stacking sequence, there are sets of web apps for that. If you want to perform machine learning for Natran, there is also a dedicated web app for that scenario also. So let's go ahead and start this tutorial. We're going to need a set of bulk data files for that cantilever beam. So open the user's guide, navigate to the shape optimization tutorial section, click on the link for starting BDF files, and this is going to download a zip file. And once we extract that zip file, we have the BDF with the cantilever beam, with the loads and the materials, and then we have a second bulk data file that is a pre-configured optimization. Before this tutorial, an objective for the weight has already been specified, and design constraints for the von Mises stress have also already been specified. What we're going to do now, we're going to open the so-called viewer web app. We're going to upload those bulk data files. So let's navigate to that directory, select the bulk data files, and click upload. And now we have our model here in the web browser. Now, if you want to manipulate or rotate or translate the model, this is how you do it. Click on the right mouse button and hold it down and drag the mouse, and you can translate the model. Left click and hold the mouse button, move the mouse, and you can rotate the model. The scroll wheel lets you zoom in and out, so let's scroll in very closely. And let's translate the model. If you want to recenter the model, here on the right hand corner or side of the window, you click on the center model, and this is going to center the model on the screen. If you click fit model, it's going to put the model all within the view. If you want to change the color, click on the background color. If you want to change the view of the model, if you want to look at it from the side or the top and so on and so on, if you want to look at it from a different angle, you can use any option in the view set of buttons, if you will. And today I'll be using the isometric view 3 option pretty often. Here in the bottom right, click on shape. This is going to open the shape panel where you can create your shapes. Click on the shapes tab. Let's go ahead and move this model to the left a little and click on this green icon, add shape. Click on the pencil icon and drag this picking sphere and select these first few elements. We'll go ahead and rotate the model, and we'll repeat the process for the bottom. We'll go ahead and select these few element faces. And you'll notice that rotation of the model is disabled when you're picking faces. Click this big orange button, and this will exit pick mode. And now you can rotate the model again. Click on this plus icon. Do you see me circle with the mouse cursor? And drag and select these elements. And the difference is the following. The primary element faces will either contract or expand, and they're colored in a darker color. The lighter colored faces are the secondary faces. These faces are going to stretch during the shape optimization. Now, let's go ahead and exit the pick mode. Let's run Nastran so we can generate our shapes. And now, in the preview table, let's experiment with different shape change values. Let's suppose that we contract the shape by -2.5. This is what that shape is going to look like. And maybe I contracted the shape too much. Let's contract the shape less. Let's use -1.5. So I'm able to preview what the shape looks like possibly during the optimization. And now we'll notice two things, or one thing about this current setup. One side, the element faces are allowed to contract or stretch. But if we look at the other side, the element faces are not allowed to stretch, if you will. So how do we fix this? Go back to the shapes table, click on the plus icon, drag the pick sphere, and select these element faces to select secondary element faces. Run MSC Nastran again, and we'll look at the difference now. Now these element faces are allowed to stretch. So whenever the top and bottom are expanding or contracting, these secondary faces are allowed to stretch. Now let's experiment with a few more other values for the shape. If we were to contract this boundary by -1.8, this is what our possible shape looks like. But suppose I go too far. Suppose I contract the shape too much. You see that the shape is going to actually start to interfere and cause a mesh distortion. If you look very closely, and here it's you can see that one of the element faces has been distorted too much. And this is not okay. Nastran's optimizer will fail that there was a mesh distortion encountered. But look what happens if I experiment with the values a little bit more. Here, if I contract the shape by -1.8, this is what the shape looks like. But here, if I inspect the elements, maybe I don't want the elements to distort this much. So let's go ahead and look at the change when we use negative 1.5. And after we look at this, maybe from personal judgment, we'll say, okay, this is the most shape change I can get. So let's go ahead and copy this value. And we'll say that this is my lower bound for the shape variable. I never want to go and do a contraction more than negative 1.5. Why? Because I might get a mesh distortion. Now, what about for the upper bound? What happens if I expand the shape by positive 2.0? Let's look at what happens. Here, this line is the original boundary. If we move this shape by 2.0, this is what I will have. Here, maybe I'll say that, you know what? I don't want to expand beyond my original shape. So what I'll do is I'll test the original bound or a value of 0.0. 0, or rather a shape change of 0 means that you're not doing anything with the shape. So here what we're going to say is the upper bound is 0.0, meaning we're not going to have any expansion for this shape. Now, let's go ahead and repeat this process and create a new shape. Click Add Shape, click the pencil icon, select these element faces, repeat the process for the bottom of the cantilever. So this is going to be our second region that's going to be allowed to expand or contract. Now, one important thing we have to do, we have to select element faces that are going to stretch, the so-called secondary faces. Now, this picking sphere might be a little too small, so let me go ahead and increase the radius of the picking sphere. And let me go ahead and move the picking sphere and select these other faces. Let me exit the pick mode and rotate the model and click on the plus icon again and select these faces. Now, suppose you accidentally select too many faces like I did here. Click on the right hand button and now the picking sphere turns red. If you now drag the sphere, you deselect faces. And now let's go ahead and look at my primary darker color faces and my secondary lighter color faces. That's what that looks like. Mark both of these checkboxes to display all the shapes that have been defined. You'll notice that we only see the primary faces, the faces that will expand or contract. If you want to look at the secondary faces, you have to click on these plus icons to view them. But when you mark these other checkboxes, just know that the secondary faces do exist, just that they're not colored currently. Let's run MSC Nastran. Let's create our new shapes. And again, let's experiment here. Let's test shape changes to make sure I do not get a mesh distortion. And here I'll see that if I contract the shape by negative 1.5, I'm not most likely going to get a mesh distortion. So what I'm going to do here is I'm going to copy the bounds here and here. So at most, I'm going to contract by negative 1.5, and at most, I'm going to expand by 0, meaning that there's not going to be a expansion for these shapes. Now remember, make sure to experiment with this. Test values for your lower bounds. Make sure you don't get a distortion like you are here. If you click on this button, look inside, you can see if there's ever a moment where you get a intersection or a mesh distortion. Here you can see that the top boundary for shape 2 is okay. It's not intersecting the lower or the bottom boundary, if you will. But notice what happens. Here there is an intersection. This is where you might get a problem. So let's go ahead and experiment with a different bound or value for the shape. And we'll go ahead and repeat the process and we'll look inside. You'll see that the top boundary is not intersecting the bottom boundary. This is what we want. We want to avoid the mesh distortion as much as possible. Now, let me click on download and download the new set of bulk data files. And now we can perform the optimization. Now we've added the design variables for the shapes. And we'll go ahead and click Start MSC Nastran to start the optimization. And if I look back here in the viewer and click on the new entry section, I get a summary of the changes that have been performed to the bulk data file. These are the only changes that have been performed to the bulk data file. And there have been some include files like the auxiliary model, p-solid, and so on and so on. Just know this. All the entries for the auxiliary model and the subcases for the auxiliary model have been added to the bulk data files. If you can, on your own time, you can explore these bulk data files and see exactly what it looks like. One comment while I open this file. By default, when you generate your DVB shape entries, the scale factor is 1.0, which is the default. When you click Run MSC Nastran here, the web app automatically decides optimal values for the scaling factors. If you ever use a value of 1.0 here, you are most likely setting up your shape optimization incorrectly. It's not correct. You should be using ideal scaling factors. The web app will automatically pick the scaling factors for you as long as you run MSC Nastran in the web app. If you don't do that, it's up to you to pick optimal scaling factors. So here in the presentation, look in the appendix. It will explain how to pick the scaling factors manually. Now let's go back here and look at the optimization results. There are two questions you should ask yourself whenever you look at the results. Number one, are you minimizing or maximizing the objective? Here, I see that I minimized the mass from 80 to 36.77. Second question to ask, do I have a feasible design at the end? A feasible design is when you satisfy all the constraints. Internally, each stress constraint is going to have a normalized constraint for the upper and the lower bound. Each normalized constraint should be negative, meaning you're satisfying that upper or bottom or lower normalized constraint. Here at the very end, you get a value very close to 0. If your max normalized constraint is negative or very close to 0, you have a feasible design. This is confirmed with the final message, run terminated due to hard convergence. So here, if we look at the max normalized constraints, we see that we have a negative max normalized constraint. It's feasible, it's positive here, so it's infeasible, 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 possibly infeasible or feasible, depending on how close it is to 0. But the important part is that by the end, we get a max normalized constraint value of 0.0001, 524,549. So this is very close to 0. So we have a feasible design at the end. Now for design variables, here we have a value of 10. Here we have a value of 10 and 8.5 for the shape variables. This does not mean you move the shape by 10 units of length. Suppose the shapes are in millimeters. This does not mean you move the shape by 10 millimeters. This does not mean you move the shape by 10 millimeters or 8.5 millimeters. This is how you interpret the shape. The difference between design cycles is how much the shape has changed. So if I go back here to the PowerPoint, let's look at design cycle 1, if you will. After design cycle 1, the delta, if you will, is 0. There's no change in the shape. What happens after the first design cycle? You see that from design cycle 1 to design cycle 2, there has been a change in the value. So before we had 10.0, and now the new value is 8.5. So what's the delta or the difference? It's negative 1.5. So the shape for Y1 has been contracted by negative 1.5. So this is how you interpret the design variables. Look at the deltas. Look at the differences between design cycles. This is going to tell you if you've expanded or contracted the shape. Negative differences mean you've contracted the shape. positive differences mean you're expanding the shape. And I think on this slide, I showed you what the total shape looks like from design cycle to design cycle. So here for shape 2, we've contracted the shape. For design cycle 2, we've contracted the first shape. And then after that, it's a combination of expanding and contraction for shapes 1 and 2. Now, you might be asking, hey, how do I get images of these different shapes? So this is where we now get to open a pre-post processor and we get to look at the results. Number 1, how do you get a result file? If you look inside the model.bdf file, we see this entry, MDLPRM-HDF5-1. This is going to output an H5 file. I recommend using the first option. From experience, I've had some issues with the second option. So again, use the first option whenever you want to look at your shape results. Let's import that Cantilever model. So we're going to go ahead and upload the bulk data file, model.bdf, and we're going to import the HDF5 file. So if I look at model.h5, select that and click apply. Let's rotate the model a little. And let's look at the results we have here. So click on the results tab, click on the deformation icon, and here on the right, we have many rows. And let's quickly describe what these rows mean. Let's suppose we have letter M shapes. So we have 2 shapes here. The last M rows, the last 2 rows correspond to the shapes that we've created. Let's select the second to last shape, which is going to be shape 1. Click on displacements here and click apply. This is the first shape that we created for shape 1. The second row, which is the last row here, this is the second shape that we created. Next, the first N, letter N, these are going to be the N design cycles that we had. Here we have 8 design cycles, so the first 8 rows are going to be the shape changes for the first 8 design cycles. Let's select the first row and click apply. This is what my first shape change looks like. It's a little hard to distinguish the original and the new shape. Click on the third icon or the third tab here, and let's change a few of these options. For the undeformed, let's click on free edge, render style free edge, click apply. So now we have the original shape in blue. For the render style, let's color the elements. So we'll click render style shaded, and now they're colored, but maybe we want to select a different color. Click on deformed, and maybe let's pick orange. Click apply. And one other thing, for the scale interpretation, always use the true scale for the shape change. Click on apply, and this is what the shape looks like after design cycle 1. Click on the first icon or tab, click on the second row for design cycle 2, click apply. This is what the shape looks like after design cycle 2. You can go ahead and repeat the process for each row. One other thing, the suffix of the row, if you will, has D1, D2, D3. This is for design cycle 1, 2, 3, all the way up to design cycle 8. So here, this is what the final design cycle looks like. Let's go ahead and select all the design cycles. So select all the rows, select shape change. Make sure the rows are blue in color. So always make sure the rows are blue in color. Click animate. On the last far right hand button or tab, click that. Click apply actually. And now we're using 8 frames to animate this. Here we have the results tab. Click on the results tab. For the number of frames, type in 50 and click apply. So now we have a smoother animation, if you will. In this animation control tab, you can either pause the animation and manually move the frames with the slider, or you can unpause the animation. If the animation is too fast, here in the slider for animation speed, you can slightly move the slider leftward, and that slows the animation. If you want to exit the animation, click on Unpost Results Tools, and now you've exited the animation. Now, one other thing you might want to do, you want to look at what the maximum von Mises stress values are. So if we look here in the plots, out of all the von Mises stress normalized constraint values for the upper and the lower bound, only one of those constraints is going to be the controlling constraint, if you will. And that max normalized constraint is plotted here. And there's only one controlling normalized constraint for each design cycle. So now you might be asking, okay, these are unitless constraints. I want to know what my von Mises stress constraints values are. If you go back to the list of web applications, click on responses. Let's open the so-called F06 file. Whenever you perform an optimization, you get information about the design optimization cycle. You'll see this table called design constraints on responses. And you'll see these values here. These constraint values are normalized constraint values. These are unitless constraint values. You have a value for the upper and the lower bound of that von Mises stress value. In this other table, that's called responses in design model, there is a table for stress responses. Here you also have input and output values. These values are in stress units. These could be megapascals, Pascal, or PSI, or some other unit of stress, if you will. What you need to do, you need to manually combine the unitless normalized constraint values with the unit values. Alternatively, you can import the F06 file here, and this web application will do this automatically for you. So here you can see all the von Mises stress values with the respective normalized constraint value. So remember, there's going to be a max normalized constraint value for the upper bound and the lower bound. Since we only specified an upper bound for the stress constraint, we only see normalized constraint values for the upper bound, if you will. Now, we want to look at the controlling constraint for each design cycle. Click on this button, maximum constraint for each design cycle. This is going to give you the controlling constraint for each design cycle. If you look at the column for normalized constraints, you're going to see that these are corresponding to the values in this plot. So it's negative 0.01, 0.13, 0.21, or 2.17, and that's what we get here. Negative 0.01, 0.13, 2.17, and so on and so on. If you click on this icon, the show more information icon, we actually get told which element is producing the highest von Mises stress. So now let's go ahead and look at the max von Mises stress for the initial and the final design. So here we see that for the initial, it's 197 units of stress, and for the end, the final von Mises stress is 200 units of stress. So let's go here, go to results, click on fringe. These next two rows are the analysis from, or the results from your actual statics analysis. Since we have an initial and final design, we have two rows. So it's one subcase multiplied by the initial and final designs, so 2. So we have 2 rows. You will have more rows depending on the number of load cases you have. So let's look at the results for the initial design. So we'll go ahead and click on stress tensor here and click apply. And now we want these values to match up to what we have here. So we need to turn off averaging. Click on this fourth icon and click none for averaging. So for domain, select none and click apply. And then one thing we might want to do here is maybe show the label. So click on the third icon and click show fringe label, click apply. what we want to do is look for the max von Mises stress, which is going to be in element 71. So let's look here and see if we can find that element. And let me make sure I've selected the right value here. And what you can do actually, let's turn on the labels for the elements and click apply. And let me look for element 71, or what I can do actually here. In the second button, click on elements and select element 71 and click apply. And let's zoom in a little. Here you're going to see that the max von Mises stress at one of the corners of the element is 198 and matches the value that we have here in the F06 file. What about the final value? Here we see that it's element 73 that's producing the highest von Mises stress. So let's zoom out a little. Let's type in 73 here and click apply. And if we zoom in a little, and remember, right now we're looking at the initial design. Let's select the second row and click apply. Now we see that this corner of element 73 is producing the highest von Mises stress of 200. So that's a way of confirming or verifying that your von Mises stress values are constrained. Now, I believe we are pretty much done with this exercise. Let me do one last thing. Let me just animate this one last time. Just go ahead and animate this. Right. So that's the end of this tutorial. I hope you found this very informative. And let me leave you off with one last thing. Be sure to refer to the appendix where you're going to find some answers to some of the most commonly asked questions when it comes to shape optimization. And if you have a question on how to perform shape optimization, you are more than welcome to contact me at this email address. With that, I'll stop here and thank you so much for watching.